In this video, we are going to discuss phase changes. So first of all, what is a phase change? Well, it's a change in the physical form, but not the chemical identity of a substance. So unlike in a chemical reaction where we form a brand new substance, a phase change, a substance changes from one phase to the next, but the actual chemical identity of the substance remains the same. So each phase change has a unique name. For example, solid to liquid, a substance converting from the solid to a liquid, is called fusion or melting. So take a minute and familiarize yourself with the names for each of these different phase changes. For example, a gas to a solid conversion is called deposition. Another thing that's important is that a couple of these occur at the same temperature, of course. The melting point of a substance and the freezing point of a substance, those are the same. So water freezes at 0 degrees Celsius and it also melts at 0 degrees Celsius. Same thing here. For example, water boils or vaporizes at 100 degrees Celsius and 1 atmosphere of pressure, and it condenses or goes from a gas to a liquid at 100 degrees Celsius, and of course 1 atmosphere of pressure. So let's take some time and discuss the thermodynamics involved when a substance undergoes a phase change. The first thing we want to appreciate that a phase change is an equilibrium process. So let's look at this one first. When a substance is going from a solid to a liquid or a liquid to a gas, when it's melting or freezing, the rate of fusion and freezing are equal. So let's use water as our example. At 0 degrees Celsius, water is freezing to form ice, and the ice is melting to form water, liquid water. So at the freezing point or melting point at 0 degrees Celsius, water is in both the solid and the liquid phase, and the rate of conversion from solid to liquid or liquid to solid, these rates are equal. So you have an equilibrium process. And that's true with water, but it's also true with any other substance when it's at its freezing or melting temperature. Same thing when you have a substance that is at its boiling or condensation temperature. The rate of vaporization and the rate of condensation, those are equal. So the substance exists both in the liquid and the gas phase, and the rates of conversion between the two phases are equal. And so we call that an equilibrium process, when the rate of one phase change and the rate of another phase change, the reverse process, when those rates are equal, the process is said to be at equilibrium. Now, as far as the thermodynamics, every chemical or physical process, and therefore every phase change, has a delta G or a free energy value associated with it. And that's what we want to take a few minutes to discuss. Remember that Gibbs free energy, or the change in free energy for a process, be it a phase change or a chemical reaction, is given by this equation, which we'll discuss more in just a minute. But the delta G value for that process, if delta G is negative, that process will occur spontaneously. If delta G is positive, then that process will not occur spontaneously. If a process is at equilibrium, then delta G is equal to 0. And that's true for a phase change or anything else, any chemical reaction. So when we're referring or talking about phase changes, it's important to appreciate that the delta G value for any phase change, when a substance is at that phase change, is undergoing the phase change, the delta G for that process is 0. That's because you have it's spontaneous in one direction and spontaneous in the other. So basically the overall process is neither spontaneous nor non-spontaneous. So let's look at delta G for a phase change in a bit more detail. The factors that affect delta G, we have a delta H, a T, and a delta S. Our delta H value is the change in enthalpy. Remember that the change in enthalpy is basically the heat that's released or absorbed from a reaction or a physical process at constant pressure. So every process, or almost every process, will release heat or absorb heat when it's undergoing a chemical reaction or some physical process, such as a phase change. The temperature also affects the delta G value, and the temperature must be on the Kelvin scale. And finally, the entropy change also affects the delta G value for that process. Remember that entropy is a measure of randomness or disorder from a chemical reaction or a physical process. So let's look at each of these in a touch more detail. Let's start with the enthalpy change, or delta H. For enthalpy in general, uh, heat is always going to be released when chemical bonds or intermolecular forces are formed. So anytime, let's take a phase change, for example. If a substance is undergoing a phase change, when chemical bonds or intermolecular processes are forming, heat will always be released. And we say that when heat is released, the delta H value will be negative and it's exothermic. If a process is going to break chemical bonds, heat is always going to be absorbed. So heat is absorbed when chemical bonds or intermolecular forces are broken. So if a process is undergoing a phase change and chemical bonds or intermolecular processes are being formed, then our delta H value will be positive, which indicates that heat is being absorbed, and we say that process is endothermic. So be sure you're familiar with this. This is very important, and these terms and the signs for delta H. Let's take a look at entropy change. Reactions or physical processes, such as phase changes, that increase in randomness have a net increase in entropy. So for example, if a substance is going from a liquid to a gas, well, you're getting more random, and so delta S would be positive. Reactions or physical processes that decrease in randomness. So if the substance is being condensed, maybe from a gas to a liquid, well, then you're losing some of the randomness and disorder because liquids are more ordered than are gases, and solids are even more ordered than those two. So a process that decreases in randomness, we say has a negative delta S value, and it's decreasing in entropy. So take a minute and look at each of these phase changes. For each phase change, predict whether the delta H will be positive or negative, and also whether the delta S value will be positive or negative. So for example, sublimation, going from solid to a gas, would this process have a negative or positive delta H value associated with it? And with the delta S value for this process of sublimation, would that phase change have a negative or positive delta S? Pause the video and predict the delta S and delta H values for each of these processes, please. Okay, so let's take a look at these. First of all, let's take a look at sublimation, vaporization, and fusion or melting. These three processes have a couple of things in common. First of all, when we're going from a solid to a gas, we have to break intermolecular forces or chemical bonds, depending on what substance we're talking about. If we're talking about water, for example, we have to break hydrogen bonds in order to get the substance to sublime. Going from a liquid to a gas, again, we have to break intermolecular forces. And going from a solid to a liquid, we have to break intermolecular forces. So for each of these processes that I have circled here, we're breaking intermolecular forces. And so for that process, it requires energy or requires heat. Remember, we talked about enthalpy previously. We said anytime a process breaks intermolecular forces or chemical bonds, heat is required, and the delta H value will always be positive. So each of these um, process that I have circled here, the delta H values will all be positive. Now the delta S values, of course, we're going from a less random state, solid to a gas, liquid to gas, solid to liquid. We're going from a more ordered state to a less ordered state. So the molecules have more freedom to move around in the final state than they do in the initial state. So we're increasing the randomness. That we're getting more random in the final state than we are in the initial, and so delta S will be positive. So for the ones that I have circled here, the delta S values will be positive. Now for the other ones, the ones I don't have circled here, let's underline those: deposition, condensation, and freezing. Here we're going from, basically it's the opposite. Our initial state is a less ordered state, more random, and we're going to a more ordered state. So in order to do these, go from gas to solid, gas to liquid, or liquid to solid. For each of these, we have to form intermolecular forces, right? We're condensing the substance or freezing or deposing the substance. So we're forming intermolecular forces. Anytime we form intermolecular forces, our delta H value will be negative. So anytime you form intermolecular forces, heat is released. So our delta H value will be negative for all of these that I have underlined. Of course, the delta S value, as we mentioned before, we're going from more random, more disorder to a more orderly state, so the delta S value will be negative. So it's important that you can appreciate the signs of these and also appreciate why the signs are positive or negative. And remember, the delta H and the delta S values, those are two of the major factors that influence the delta G value. Those ultimately will determine whether a process is spontaneous or non-spontaneous. The delta H, the delta S values, and of course the temperature also plays a role, as we mentioned before, in determining the delta G and ultimately the spontaneity of a process. A couple more things, a couple of definitions real quick. The energy that it takes to melt a substance, for a substance to undergo the fusion process, is what we call the enthalpy of fusion. The enthalpy associated with the vaporization, so basically how much energy it takes for a substance to be converted from a liquid to a gas, is also called the enthalpy of vaporization. So the enthalpy of fusion and the enthalpy of vaporization are two important terms that you want to appreciate. So be sure you write these definitions down. The enthalpy of fusion, the amount of energy required to overcome enough intermolecular forces to convert a substance from solid to liquid. And again, going from solid to liquid, we're breaking intermolecular forces, so the delta H value would be positive. The reverse, if we were going from liquid to solid, the value would be the same, but it would be a negative delta H. And the amount of energy required to overcome intermolecular forces to go from a liquid to a gas is what we call the enthalpy of vaporization. Again, we're having to break intermolecular forces, so this value will always be positive. If we're going from gas to a liquid, therefore we're forming intermolecular forces, and that value would be the same numerically, but the sign would be negative. So be sure you appreciate the signs of enthalpy and entropy. It's very important for phase changes. And one last thing, let's talk just briefly about the temperature. Remember our Gibbs free energy at the freezing or boiling temperature, the phases are in equilibrium. So if we look at our Gibbs free energy, the process that is at equilibrium, such as a phase change process, our delta G value, as we mentioned before, is always 0. So we can rewrite our Gibbs free energy equation and replace our delta G value with 0. Now remember, we can only do this when we are talking about a substance that is undergoing a phase change. If it's not at a phase change, then the process is not at equilibrium, and we can't make this assumption here. So if we have our delta G value set to 0 because we have an equilibrium process, we can rearrange this equation to solve for T. So we can solve for T And whether we're talking about the freezing process or the melting process or the vaporization process, we can solve for the T, which this would represent our freezing temperature or our melting temperature, and this T would represent our boiling or our condensation temperature. If we're using the delta H of fusion or delta S of fusion, or here the delta H of vaporization, delta S of vaporization. So basically, we can rearrange this equation to solve for the freezing or the boiling temperature if we know our delta H and our delta S values. So that's very important. So be sure you appreciate the uh, phase changes and the thermodynamics involved in all of these phase change process.